The term chi-square test refers to any hypothesis test based on a distribution called the chi-square distribution. The chi-square test to be described in this section is a chi-square goodness of fit test, which is used for comparing counts of a categorical variable with a hypothesized set of counts. Two other related chi-square tests, which will be described in a later section, are a chi-square test of independence and a chi-square test of homogeneity, which are tests that involve two categorical variables. There are several other quite different tests that are also called chi-square tests, but the tests to be covered here and in the next few sections are among the most common. To describe the chi-square goodness of fit test, here's a table showing data collected to find out if bees are more attracted to certain colors of flowers. This table shows the proportion of each of 5 different colors of flowers in a flower bed and the counts of the number of bees attracted to flowers of each color. If the bees have no particular preference for one color of flower over another, then it's reasonable to expect that the proportion of bees attracted to each color will be the same as the proportion of that color of flower in the flower bed, so that expectation becomes the null hypothesis, which is that the proportion of bees attracted to each color of flower is the same as the proportion of that color of flower in the flower bed, and the alternative hypothesis is that one or more of those proportions are not the same. The categorical variable in this example is the color of the flower that attracts each bee. The total number n of bees in all categories is 130, and the expected counts in each category under the null hypothesis is n multiplied by the proportion of flowers in that category. The test statistic to be used here is the sum over all categories of the square of the expected bee counts under the null hypothesis for flowers of each color minus the actual observed numbers of bees that were attracted to that color divided by the expected counts. This statistic is traditionally denoted by chi-square. This statistic is a measure of the difference between the actual data and the null hypothesis, since the sum increases the further the observed counts are from the expected counts. The sum is 0 if the observed count is exactly equal to the expected count in every category, and the result is always non-negative. Using the observed counts and the expected counts from the table, the chi-square statistic can be computed following the formula by totaling the squares of the expected counts minus the observed counts divided by the expected counts. If the sample size is big enough, the distribution of this test statistic is well approximated by a chi-square distribution. The sample size is generally considered big enough for this approximation if the expected count in each category is 5 or larger, and that condition is satisfied in this example. The particular chi-square distribution to use here depends on a quantity called degrees of freedom, which is one less than the number of categories. In this example, there are 5 categories since there are 5 different colors of flowers, so the number of degrees of freedom is 5 minus 1, or 4, and the sampling distribution is a chi-square distribution with 4 degrees of freedom. Here's a plot of that distribution with the value of the test statistic shown on the plot. The p-value of the hypothesis test is the area in the tail of this distribution, which can be computed using the cumulative density function CDF of the chi-square distribution with 4 degrees of freedom. This p-value is about 2.7%, so using a significance level of 5%, the conclusion is to reject the null hypothesis and conclude that the proportions of bees attracted to certain colors are not all the same as the corresponding proportions of colors in the flower bed. This test does not indicate which colors of flowers tend to attract bees. Rejecting the null hypothesis indicates only that the proportions are not all the same. Finding out which colors attract bees would require a separate look at the data. Also, unlike the hypothesis tests in earlier sections, this test is always a one-tailed test. The test statistic increases for any difference between observed counts and the null hypothesis, so only the tail on the right is of interest for deciding whether to reject the null hypothesis. Conditions for the validity of this test, including the condition that all of the expected counts be at least 5, will be covered in more detail in the next section.